So this is the plastic track. Right now it has an inclination of 10 degrees. So this is the protractor that measures the inclination of the track. And we're going to use that data to do some calculation later. And this is the smart card. So it has built-in force and motion sensors, and it can measure instantaneous force, position, velocity, acceleration, and will create real-time position time graph, velocity time graph, acceleration time graph. And you can connect your phone through Bluetooth with the card using the SparkView app. I will show you in a second. And then you can get those graphs or the data on your phone, and the students can use them to do further analysis. So with this lab, I'm going to do a quick demo, show you how to use smart card to have students verify the law of conservation of mechanical energy. So basically, I'm doing a demo lab. And it's quite simple. You just let the car roll down the track. And then with the data collected, students can verify if the mechanical energy is the same along the way. Okay, so let me first show you how to connect the your phone with the smart card. So let me share my screen first. All right. So you need to download the SparkView app, okay? And then you open it. You can choose build new experiment. And then choose the first layout. I normally just use the first layout, the one on the very top. And then choose the graph option, which is the very first option. All right. Now you need to choose Bluetooth icon on the top, Bluetooth. So I'm going to turn on the card. And then it shows up here. So you can click on that to connect. Don't choose update, just cancel it. The update takes forever and it's not needed. All right, so now you're able to see, if you click on select measurement, you're able to see all the quantities that are being measured, position, velocity, and acceleration. So I'm going to put the position on the screen. So right now, even position is on the main screen, but velocity and acceleration are also being measured. And later, you can also get the data and the graph of those as well. Okay, so you can also adjust the frequency on the bottom left corner. So normally I use 50 Hertz, which is the frequency of the ticker timer in the lab. I think that's a good frequency. But you can also choose 20 Hertz, 30 Hertz if you want. And then you'll just put the car on the track, click the green button start, and then you'll just let the car go and click stop once the car hit the stopper at the end. So I'm going to go ahead and do that. All right, so that's it. Now I'm gonna show you how to analyze the data and the graph in a bit of greater details. So let me first Okay, so let me first turn off my audio, my video. So this is the position time graph. And as you can see, it's a pretty nice parabola. So this is a constant acceleration motion, and the position time graph is supposed to be a parabola. And let's pull out the velocity time graph, and you can see it's a straight line. And so the velocity is increasing at a constant rate. And as can be seen from the acceleration graph, and the acceleration is constant, right? And you'll see some like other weird stuff at the end. We can actually ignore those because I'm just gonna look at the part where the card goes down, right? So this is when the card bumps on the stopper, then goes back up. So the velocity is gonna decrease and go into the other direction. So the same with position. So I'm gonna just look at this part when the position increases steadily until it hit the stopper. Then after that, it bounce back up, right? So, but I'm not looking at that part, just this part, when the position increase steadily, and when the velocity is increasing at a straight line, right? This part. And the idea is basically, let me go back to position. Yeah, I know I'm switching constantly between position PT and VT graph. So the idea is pick any 2 points along the way and you calculate the total mechanical energy, which is kinetic energy plus gravity potential energy at each point, and then you compare them, right? So ideally, they should be the same. So like some people like to pick the initial point when the position is 0 and the ending point when the card gets to the bumper. But I noticed that with the smart card, the beginning and the end, the data is kind of tricky because, for example, at the beginning, when you release the card, you may accidentally push or pull down it, and that'll apply a force on it, which will change the energy of the entire system, right? So at the beginning, the data I find is not very reliable. So I recommend you to pick points in between, right? So I'm gonna show you the 2 points I picked. So I picked one at 0.16 second. Actually, I'm gonna use another experiment I did. It's the same experiment with slightly different data, but that experiment, I already analyzed the data, so I can save some time and give you a bit more information. So I'm gonna use this one. Right, so this is the data I get from basically another trial, and I already analyzed this trial. So I'm gonna use this one. So you can see it's the same thing, right? The position is steadily increased and then it bounced back up, but I'm gonna use the first part. So the 2 point I picked is 0.16 at 0.16 second. And another point I picked is 0.26 seconds. Okay, so basically I'm looking at 0.16 second, what is the total mechanical energy? At 0.26, what is total mechanical energy if they are the same? Okay, and from PT graph, I get the position, and from the VT graph, I can get the instantaneous velocity, right? So the way you pick the point is you just click on a point, then click the very left icon. That'll show you the coordinate, so 0.16, and I get my velocity data, 0.37. So I already wrote it somewhere else. I recorded it because I need it later for calculations. And then 0.26. And so you can like click go forward, go backwards to move to the next or the previous data point. So I'm going to move to 0.26. So that's the velocity at that point. So with those velocity data at 0.16 and 0.26 seconds and the position data at those two points, I can actually start doing the calculations. Okay, let me pull out. All right. So basically the idea is here I have slope, and then so the card, let's say start from here and end here. So you can calculate the mechanical energy here and the mechanical energy here, the total of kinetic energy and potential energy, then compare them, right? But like I just mentioned, the initial and the end, the data is a little bit tricky. Sometimes it's not very reliable. So I'm gonna pick 2 points in the middle. So I'm gonna verify the mechanical energy here and compare to the mechanical energy here. So this, let's call it just point 1. This is point number 2. And this is time 0.16, as I just showed you on the graph, seconds. And at point 1, the position is 0.0435 meters. And the velocity, I'll just call it v1, equals to 0.37 meters per second. Okay. And t here, the point 2 is 0.26 seconds. Position 0.0888. V2 equals to 0.534. Okay, so I'm going to use those data to calculate the mechanical energy, which is equal to kinetic energy plus potential energy at point 1, and then later at point 2, then I will compare. Okay, and so kinetic energy is equal to, at point 1, it's equal to a half v1 square plus potential energy mgh1. Okay. So here I have a technical comment. So technically this is h1, right? This is h1, and then this is h2. But I find if you're gonna do that, you have to literally use ruler to measure the height. And when you use ruler to measure the height, you introduce more errors. So I don't think that's a good method. So instead, we don't do this. We use the position data to figure out the relative height. So I'm gonna basically make this my zero potential energy reference ground. So I make this like my artificial ground. So I don't need to worry about potential energy at point 2, that becomes 0. And I'll just get the height here. This is gonna be h1. So relative to 2, at point 1, there's going to be a gravity potential energy. And this h1 is in this right triangle. And this is the 10-degree angle of inclination. And the position here can be calculated by taking the difference between the two positions here, right? Because P1 is, this is 0.0435. So this is P1 from the beginning to 0.1, and P2 is from beginning to 2. So this is 0.0888 from 2 to beginning. And their difference is going to be between 0.1 and 0.2, which is the hypotenuse here. And then I times sine 10 degree, and I can get the opposite side. So this is a bit trigonometry. Good math review for them. They should have learned this in Math 10 already. And then I can calculate the mechanical energy here at 0.1, and similarly at 0.2. So then I will compare if they are the same. All right, so I'm gonna go ahead and plug in some numbers. So a half, the mass of the card without accessory is 0.245, and the V1 is 0.37 square, and plus 0.245 times 9.8 times H1, which is sine 10 degree times the difference between the two position 2 minus position 1. Right. So again, this gave you the hypotenuse and times sine 10. This is trigonometry. You get the opposite side, which is H1. So this entire thing give you H1. Right? So you're not taking any actual measurement with the ruler, because the entire point of using smart card is to be able to use the data, the sensor from the smart card as much as possible, because it's actually quite accurate, as you will see later. So avoid using mechanical measurement like ruler or like a timer on your phone. So this is the way to avoid that. But of course, like some students, if they want to do it that way, they can totally measure the actual height of 0.1 and 0.2. But then they have to identify 0.1, 0.2 on the slope, which is another tricky thing to do. So I highly recommend to do it this way, and assuming this is the zero potential energy, because eventually you're comparing the relative mechanical energy between the 2 points, right? So you can make anywhere you zero potential energy. It doesn't have to be on the ground. All right. And then after I do the calculation, I get 0.035657 joules. And then I just give it a little bit more digits to be more accurate. So this is the total mechanical energy at 0.1, And then I'm gonna do the same thing with 0.2, K plus P at 0.2. So at 0.2, KE is a half mv2 squared. There's no P, right? Because I made 0.2 the zero potential energy reference ground. So the mechanical energy is just equal to kinetic energy, which is a half 0.245 times 0.534 squared. And the answer is 0.034932 joules. Right. You can already see those two answers are quite close. But to find out actually how close they are, we need to get the percentage error. So this will give you an idea of what percentage error is there in your calculation. So this percentage error is equal to the difference between the data divided by the initial value. So the initial mechanical energy is 0.035657, and the difference is between those two values. So we're gonna do the difference first and divided by the initial 0.035. So note here, you're not only calculating their difference, you're actually calculating a more accurate value to represent the actual error, which is the you need to divide by the initial and see the difference compared to the initial value, what percentage is it, right? So that's the most accurate way to represent the error in your experiment. And you will get 0.02, which is 2%. It's actually very close. They are essentially the same, right? Your percentage error is only 2%, which means that the difference is only 2% of your initial data. So they are fairly equal. They are very close. And then the students can try to explain why there's a 2% error. Hopefully, they can think of the energy loss due to heat, because when the card comes down, there's going to be friction on the card, also maybe some air resistance. All of those will cause the mechanical energy to be lost to some heat energy, right? So, but that doesn't mean energy is not conserved. It just means the energy is transformed from some kinetic energy to heat energy, right? So this is also a good place to talk about like energy transformation. So this 2% is kind of expected. They cannot be exactly equal because there is energy loss, okay? But since there should be minimum energy loss, since the track is very smooth, so they should be able to see the two values are quite close, which they are seeing here, which proves the law of conservation of mechanical energy. And they can also do some qualitative analysis, like they can tell at point 1, the energy is greater than at point 2, right? So which means some energy is lost along the way. Yeah, so this is the one for the law of conservation of energy.